to non-imaging optics. So today, yeah. So first we need to understand what does non-imaging optics actually mean, and how does it compare to imaging optics. So before we jump into non-imaging optics, we want to try to understand what imaging optics means. So let's take a quick review on what this is. So imaging optics is what you have been talking about the last 2 weeks or so, particularly with geometrical optics. So you learned the laws of reflection, laws of refraction, Snell's law, and so on. And as well as you thought about various components like lenses, mirrors, prisms, and so on and so forth. And you also done some homework problems on this. You've also, there was a practice problem set that it cut the poster as well. So all of these are important for you to gain some intuition as you work through these problems. But the common thread in imaging optics is the fact that there is a one-to-one mapping from the object to the image space. So if I were to make sure I can, oops. Okay, here we go. So my marker is not working quite. Let's see. There's a one-to-one mapping in imaging optics. What that means is that every point on the object then gets mapped to one point on the image. So, okay, now it's working. Sorry about that. So if you think about a point here on the object P, that gets mapped to a point P prime on the image, and no other point in an ideal imaging system. In other words, P does not go into another 2 or more points. You know, it only goes to 1 point. So that's it's a one-to-one mapping, and that's a fundamental property of imaging systems, and of course, ideal imaging systems, as we'll see shortly. In other words, light from point P is captured by the optics and imaged onto point P prime, and there's a unique one-to-one mapping between the points in P and P prime. Okay. Now I didn't define what goes in here. This can be a lens, it can be mirrors, it can be combinations of things. Okay. It doesn't matter what it is. Think of that as a black box. In non-imaging optics, on the other hand, this one-to-one mapping is not necessary. The goal in non-imaging optics is to create a desired irradiance, which is power density, on the receiver from a given light source. So in non-imaging optics, we have a light source. We want to transfer the energy to a receiver. Now, of course, we know this light source can be the sun, it can be a lamp, whatever. The receiver can be a solar cell, it can be a human eye, whatever. Or the illuminating a room or a road if it's a car, for instance, right? So there are lots and lots of options. The key property here is that there is no one-to-one mapping. In other words, the Ikata, are you still there? I saw you.
Yeah, I'm still there.
Okay, so you joined again for some reason.
Yeah, okay. Sure, like I have joined in another device from another device.
Okay, that's fine. So the idea in non-imaging optics is that the one-to-one mapping is missing. So in other words, your aim is not to form an image, but your aim is to do this energy transfer, the power transfer. So that's the key idea that you want to keep in mind. There is no one-to-one mapping of the points of the source, from the points of the source to the receiver. Another way to think about this is that if I were to take any point here, the energy emitted by this point, of course, you can think about this going off as spherical waves, can end up in many points here. It is a one-to-many mapping. Okay, that's another way to think about this. And we'll see this again shortly. Whoops. Okay, so with that in mind, now let's think about, so first of all, before I move on, now from this simple definition, it should be obvious to you that all imaging optics is automatically a part of non-imaging optics. In other words, the imaging optics is a subset or belongs to the larger set of non-imaging optics. And we'll actually come back to that concept later on. So in imaging optics, again, if I look at a point F, the light from F is concentrated onto A, as shown here. So I have an object here, I have an image here. We know from geometrical optics that rays from F can, if it's located at the right location. So here I'm assuming this imaging condition is satisfied. So this is the object distance, right? And this is my image distance. Let's call this U, let's call that V. And if I say this lens is a focal length of F, I'm assuming that I place my V and U such that the imaging condition is satisfied. This we saw before. Now, if it is satisfied, then all the rays that come out from F here should end up at a unique point A. So that's a mapping. Now I can think about this as concentration as well. Energy from F gets concentrated into A. Okay, so that's obvious. And same thing happens here. Energy from P gets concentrated to some point Q here. Now, of course, we also know that in imaging systems, that because you're forming an actual one-to-one map, there's a magnification factor. So this size, if P is now focused to Q, this distance, this height here, D0, is equivalent to an image height DI, as shown there, right? And then DI, the ratio DI divided by D0 is called the magnification or the demagnification. So if it's less than 1, it's called demagnification because you get it smaller than the object. The image is smaller than the object. If it's magnified, the image is larger than the object. We saw that before. Now, in non-imaging optics, the equivalent concept is something called concentration. Or, there are many terms to this, or geometric concentration, and so on and so forth. And we'll see this again, but this is a very important concept. But there's an equivalent. This is magnification, right? And this is concentration. So in imaging optics, you have magnification because, again, you have one-to-one maps. You're simply expanding or compressing a particular object. In non-imaging optics, you don't do that. You simply collect the energy. We'll see these concepts again. Now, how do we design imaging systems with lenses? So we're thinking about just loss of refraction. Here an example is shown of a single point imaging one point along the optical axis. So I've drawn an optical axis here. I have a surface here that I need to design. And I have a point here that I want to map onto a point Q. Okay, so far so good. The way you would do it, of course, is that you would start drawing rays. Naively. Of course, by now you know how to do this with matrices and so on, but let's just do it naively first to gain some intuition. You'll start drawing rays. So you have a ray that goes through the surface. Now, if the tangent to the surface is perpendicular to the ray, nothing happens. It goes straight through, right? So that is the optical axis, as we know. That we can use by definition. So you can define this axis and then define everything else around it. Now I can start drawing other rays. So okay, I'm going to draw this ray here. And here again, we know how to design this because I know that if I have a ray coming this direction, I need that ray to bend such that it ends up at this point Q. Okay, that's my goal. But in order to do that, I know I need to satisfy the law of refraction. So I can define a normal here. I have some input angle, theta I, and I have an output angle, theta O. And then I know that n times sine theta O, where n is the refractive index of the material, should be 1 times sine theta I, where 1 is the refractive index of air outside, right? This. Now, from these equation and the fact that theta naught is defined, and theta I are defined with respect to the normal, that defines the normal, this normal to the surface. But the definition of the normal to the surface automatically defines the tangent to the surface or the surface itself. So if I do that for many rays, right, I can do that for an infinite number of rays. Of course, you do this with a computer, right? I can do this for many rays. All of these rays, I have to make sure that they end up at the same point, right? If I do that, I can define a tangent for every such ray, the intersection of every such ray with the surface, right? Because I now defined the normal at each of these points. I've defined the tangent at each of these points, and then I can join them all to create a single surface, okay? And of course, we're not going to do it this way because this is very tedious, right? We're going to do this with matrices or with the computer software, as you will learn next week. But the basic concept is this. Now, we all know this by now, but and this, by the way, is also called the Cartesian Oval because this is an oval. It turns out to be a parabolic shape, spherical for small angles, but further away it becomes parabolic, but not so important at this point. By definition, this is a surface that each point on it has only one ray of light from P. So another way to say it is if I take a single point on the surface, there's only one ray from P. Of course, there's only one ray. You can only draw one line. And there's only one ray that goes to Q. Now, by defining such a surface as shown here, then I can actually mathematically prove that all the rays that are coming from P in this hemisphere, this side of the surface, side of the space, will all be redirected such that it focuses at Q. This can actually be proven explicitly. So if I have a single point here, I can draw an arbitrary ray, and I can come up with a surface such that all the rays end up at Q. That's a very profound statement, by the way, which means that I can now define a perfect lens. So if I can define a perfect lens for a single point. Now, there is something called the Fermat's principle, which we will see again, but I want you to kind of get an intuition for that defines this, that also applies here. Essentially, it means that the optical path must be the same for all the rays. Now, what does optical path mean? Now, let's define what optical path means for a second. If I have a point A and I have a point B, I know, and there's nothing in between, let's say, we know that light travels in a straight line, right? So that's the straight line. Now, let's call the distance A to B L. The speed of light is, of course, C. So the time taken from A to B by the photon is what? The distance traveled divided by the speed of light. What Fermat's principle says is that the time taken by light to go from one point to another point is always the minimum for independent of what is in between those 2 points. Doesn't need to be nothing in between. Now, let me state that again. So actually, let me do another example to illustrate this concept. Let's imagine this whole thing is now filled with water, whose refractive index is n. So the speed of light in water is now c divided by n. It slows down a little bit, as we know. Of course, the physical distance is the same. It's still L. Now, the time taken by light from A to B inside the water is what? The physical distance is still the same. The speed is now scaled down, so it's slowed down. So it takes a little bit longer, right? L over C times N. Takes it takes more time for the photon to reach that location, A to B. Now, if I compare, so this is in air, and this is in water. If I compare these two, what has happened is that a distance of L in air is now equivalent in terms of the oops, my sorry, my thing is misbehaving. Sorry about that. Let's see. If you compare those two, what you will notice is that the distance, the time traveled in water is longer by a factor of n. So another way to think about it is that the distance in water is equivalent to a longer distance in air by a factor of n. Those two statements are equivalent. Let me draw what I mean by this. This is an important concept to keep in mind. So L of air is equivalent, not physically equal, but equivalent to n times L in water, where n is the refractive index of the water. When I say equivalent, that means light will take the same amount of time to travel a distance of L in air as it would to travel a distance of n times L in water. Okay, now I can define an optical path. Okay, optical path is defined now as the physical distance. Okay, so the actual physical distance multiplied by the refractive index of the medium. Of course, if the refractive index is 1, as it would be for air or vacuum, then the optical path is equal to the physical distance. Now, we all know now, intuitively, what does the optical path mean? It just means it's the equivalent path the light would have taken if that path was in air. Such that the time the light takes to go from one point to another point is the same. And don't get too confused by this. We'll use this many times, so it'll become very clear. So what Fermat's principle says, again, let me just write this down, is that the optical path must be the same for all the rays. Any photons that leave this point will reach this point with this at the same point of time. The time delay from this point to this point has to be the same. Now, the way, of course, you can mathematically write this down is that if I draw any ray, so I want to draw this ray, and the optical path in air is d plus, now I'm traveling inside some material like water. Now, optical path inside that is refractive index of that material times n times d1. Okay. Now I can draw another ray through the optical axis here. That is this capital D times 1, right? That's in air. And then I have capital D1 in water or some other material. So I can take any ray and this condition must be satisfied. Okay. Now, of course, this, if you actually work out the equation, this actually turns out to be a parabola. This is one way to prove it. So you can show that if you have 2 points, if you have a fixed optical path length between them, there is a single surface that defines that. Now, if you go to more than 2 points, it turns out such a surface does not exist. And in order to, in order to image more than 2 points, you can show that you need to have more than one surface. So let me just state that one more time. In order to image 1 point to 1 point, you can actually do this in an ideal fashion, mathematically ideal fashion, with one surface like that, one boundary. But you can't, as soon as I add another point, let's say I call it another point P prime here, I cannot do this ideally with one surface. Of course, I can do this non-ideally with one surface, which we'll come back to later. Now, if I want to image 2 points, of course, in an object, you have an infinite number of points. So 1 point itself is not that interesting. So you want to, let's think about what happens at 2 points. Now, in order to image 2 points, it turns out you need to have at least 2 surfaces. And you can think of, I mean, you can prove this mathematically, by the way, just using Snell's law, but I want you to think about this intuitively. In order to image 2 points, I need to match the optical path lengths from 2 different points. So I have a set of rays coming from this point, right, which is concentrating onto this point. And I have another set of rays coming from this point that I need to concentrate to this point. Okay. Now, if I think about it, I can define one surface to make this transformation, like I just told you in the previous slide. And I can draw another surface to make this transformation. But in the most general sense, I cannot have one surface which can do both transformations because they will have different shapes, right? I cannot define 2 different curvature, radius of curvature, for instance, on the same surface. That's not allowed at the same point. So it's a simple geometric way, intuitive way to think about the fact that if you need to transmit rays from 2 different points to 2 other points, you need to have more than one surface. So you can show that this can be done with 2 surfaces. So in other words, 2 surfaces can be designed. And another way to actually see this intuitively is that the definition of one surface is literally one linear system of equations. The definition of the second surface is a second independent linear system of equations. You can actually solve 2 independent linear systems of equations with 2 parametric functions that define 2 surfaces. So this can actually be shown mathematically. But in any case, what we need to understand is that you need 2 surfaces in order to have 2 points perfectly image F2A and E2B. Now, you can, what does this mean? This also means that if I take any other point, so I'm going to come back here and take some arbitrary point here, and I cannot guarantee that the rays that are emitting from this particular point ends up at one unique point on this side. I mean, it might be approximately true, as you know from the geometrical optics lectures, but you can actually show that it is not exactly true. Now, what does, again, does that mean? That means if you want to do perfect imaging, and when I say perfect, of course, this is a caveat. Perfect imaging means I have to take all the rays from all the points and put them onto unique points on the image side. And all the rays need to go to the unique points on the image side, such that there's a one-to-one map. You can show that you need an infinite number of surfaces and essentially a perfect control of refractive index to do this. In fact, there are some special cases where this can be done, but that requires some slightly different understanding of the physics. So we won't go into that. But from our perspective, real lenses do not form perfect images. What this means is that real lenses form imperfect images or images with aberrations. And we talked a little bit about this in the context of geometrical optics. Now, aberration theory is actually a very complicated topic in itself, and there's a whole field in itself, and we don't have time to talk about it. I want you to understand that real lenses, of course, are imperfect, not even if they're perfectly manufactured. It's nothing to do with the practicality of it, just mathematically they're imperfect. Now, another way to think about this is that adding more and more surfaces, you can actually correct for aberrations. So if you open up the camera in your phone, for instance, you'll have 6 or 7 surfaces today. And the reason there are so many, actually 6 or 7 lenses or 14 or 15 surfaces, the reason there are so many surfaces is because they're using these surfaces to correct for these aberrations. So again, another way to think about it. Of course, in that case, it's a bit more complicated because you have aberrations like chromatic aberrations, color, and off axis, and so on. But we won't talk too much about it. Now, if I were to take this picture here, and now I'm going to think of just the edge rays. Okay, so we're going to come over here. Now I'm going to think about this not as an object and an image. I'm going to think about this as a source, like the sun, and a receiver, like the solar cell. And now I'm going to say, let's consider the lens as a concentrator, or a device that converts or transfers power density, energy density, or irradiance from the source to a receiver. Now, let's try to understand what that statement means. What it means is that if the edge points E and F are imaged onto two edge points A and B respectively, which we saw before, that can be done with two surfaces, then it turns out there's a principle called the edge ray principle, which we will see again. If the edge points E and F, E is mapped to B, F is mapped to A, then all the rays from the intermediate points must pass in between A and B. Now, let's understand what that actually means. What that means is that I know that all the rays in F ends up at A. Okay, that much I know. I know all the rays in E coming out of E, ends up at B. What the edge ray principle is saying is that if I take any other point here, I can draw a bunch of rays, all those rays must end up somewhere in between A and B. It may not go to a single point, but it has to lie in between. In imaging optics, of course, if you have a perfect imaging system, it will go to a single point. But in non-imaging optics, it doesn't need to go to a single point, but it will remain in between A and B. Another way to think about this is if I have a lens that maps E to B and F to A, that's my lens. That lens is also a concentrator. It will take all the energy from the points in between E and F and assign it to points in between A and B. Not necessarily in a one-to-one manner. So in other words, no image may be formed. Now, if it's a lens, it can form an image, but need not be. And there is no one-to-one correspondence between the points on the object and those on the receiver. Okay. That is the fundamental difference between imaging and non-imaging optics. And this is, of course, if you think about this, the field of non-imaging optics is a simpler design problem in one sense, in the sense that you don't need to have this one-to-one correspondence. The one-to-one correspondence is very difficult to attain because you really need to map each point to each point and minimize aberrations and so on. However, in non-imaging optics, so that would imply that the non-imaging design problem is simpler, and which is true. However, the increase in the degrees of freedom that we have attained by removing this constraint means that the mathematics of doing that design gets to be a little more complicated. So it's complicated in one sense, simpler in another sense, and you'll see some examples later on. We'll look at some simple examples. Okay, now we will, not exclusively, but we can look at the situation where the source is large and far away, like the sun, right? So the sun is large and far away, and a lot of times that is the source of interest to us. And if that is the case, then we don't define physical distances like we did here. We don't define like a point, a size there. Instead, we will define angular extent. Because if you look at the sun is big, and if you look at it really, really, really far away, each point of the sun essentially emits a wave. But as it goes farther and farther away, and you are close to Earth, it basically looks like a plane wave. And the point from the center looks like a plane wave going straight like that. The point from the edge will look like a plane wave going like that. So if I'm an observer on Earth here, what I see is light coming at different angles. So instead of having a physical distance, I will think about angular distances. This is the angular extent of the sun. And in the case of a cloudless day, the angular extent of the sun, it turns out to be approximately half a degree. You can easily measure this. Okay, so with that, now we can think about what does that mean in the context of non-imaging optics. So, if the source is large and far away, we can define the angular extent. So here we have rays defined as d1 with an angular extent of theta1. Rays on other side. In this example, we've drawn this to be symmetric. So theta is the same and d2. And the lens DC is simply converting the rays to the receiver AB. So parallel rays A1 are focused onto A. So if we think about this as a lens, we know that, okay, I'm gonna redraw this a little bit. I should have drawn this a little bit better. I'm gonna draw this with the lens actually, since you're familiar with it. If I take a parallel rays coming on axis like that, we know the lens will focus at a distance equal to a focal length. Now I'm going to draw off-axis rays, which I believe you've also seen. I'm going to draw rays coming in at an angle. What will happen? We know that this will focus at a location which is a little bit shifted down. And it is shifted down by a very exact, precise number, that is theta. We know that this distance is f, and this distance is f times tan theta, or for small angles, f times theta, where theta is in radians. Okay, so it's exact. I mean, that's exactly what's shown in this picture here. I have rays coming in at this angle. All of them are focused to this point. I have rays coming at this angle. All of them are focused to this point. And I know, just knowing these two pieces of information from the previous slide, that if I have any other rays coming at an angle, let's say alpha, it needs to end up in between from the edge ray principle. Okay. So in summary, what we're saying is that parallel rays are D1 are focused onto A, parallel rays D2 are focused onto B. It's simple, just from geometrical optics. All the rays in between the ray angles D1 and D2 must end up at points in between A and B, but they need not have a one-to-one map, which is good. In other words, I can take the lens and concentrate the light of the sun, which we all know. So here is a way to, at least in a consistent and intuitive way, to understand it. Now, of course, the lens is a good concentrator, but the lens is not necessarily the best concentrator, because remember, the lens is forming an image, which means that you're not using all the degrees of freedom, and we'll come back to that. The best. So I want to take a short break, maybe for the 30 seconds or so before we jump into the next topic, to see if there are any questions. Ikata, is any? I don't see anything in the chat, but any questions?
Do you have any questions? She can raise. Okay, it seems to be perfect here.
Okay, good. Yeah, I mean, some of these ideas are simple, but I want you to go back and review it just to gain some intuition into it. Okay. Now, as I said before, the lens itself can be a concentrator, but it's not the best concentrator. Now, you can actually show in a two-dimensional universe, the optimum concentrator is something called a compound parabolic concentrator. So I want to spend the rest of the class trying to understand its properties and the reason and why it is the ideal concentrator. And this is important because it will gain intuition as you start thinking about your own particular projects. So to start with, I want to play a short video. Now, of course, this video is a commercial video of a commercial compound parabolic concentrator. And as I said, this is not a 2D concentrator, it's a full 3D concentrator. And let me just play it quickly. It's relatively short. And there's no audio, so I'll just narrate it. Actually, there is audio. Okay, good. That's what a CPC looks like. And this particular CPC was a solid piece of glass. It doesn't need to be that, and it operates by total internal reflection. And we'll see the differences there shortly. But I should point out, of course, CPCs are used in many, many areas, particularly, not just solar, especially these kind of very heavy glass-like CPCs are only used in telecom routers and discrete components, where you have to route light from one set of fiber optics to another set of fiber optics. This is a very efficient way to do it. Now, let's think about what are we trying to do. Our goal is to increase, of course, our goal is to transfer power. Okay, we want to transfer power from the source, whether it's the sun or the lamp or whatever, to a receiver like the solar cell or something else. That's our design goal. Our design goal is to concentrate incoming radiation to the maximum possible extent with the highest possible efficiency. So now let's think about what does that mean in the schematic. So I have a radiation source. Again, I'm going to assume that the source is shown here, E1, and I have a receiver. So I have a source here with some angular extent, and that's a spatial extent, and I have a receiver here. So if I were to think about what is the concentration factor? The concentration factor is the area of the receiver divided by area of the source. Now, this is we'll modify this definition later on, because the source might also be just the area of the collector and so on, but that's one way to define it, right? Now, of course, in order to increase this concentration, actually, sorry, I should have, this is not true. It should be the source on top and receiver at the bottom. Source or collector on top. So it's inverse. So in order to have a very high concentration, of course, I need to collect from a big source onto a small receiver. So that's intuitive. Now let's think about a source really, really far away. Okay, so I now have a very simple situation like we saw with the solar cookers. I have two mirrors. Actually, let's start with just one mirror first. I have a mirror defined. So first, actually, before I define the mirror, let me define the receiver. So I have my receiver here, AB. Okay, this can be my black body. This can be my solar cell, but I'm going to call this a receiver. I'm also going to call it an exit aperture, because that's where the light is exiting. Okay. Next, I'm going to place, and I have an input. My input is this ray right here. I'm going to just look at one ray. This will be an edge ray, as we will see later on, but I'm going to just look at one ray, coming at an angle theta to the normal, shown here. Now, what I need to do is because it's an edge ray, I need to ensure that this ray ends up at one edge of the receiver. So how can I do that? I can use a mirror. So I'm going to use a mirror here. Okay, these lines here indicate that it's a mirror placed at an angle beta to the horizontal, such that this ray comes in, intersects with the mirror, follows the law of reflection, and goes over to the edge of the receiver, in this case, the edge A. Okay, so all I have to do is I have to pick this angle beta from a given known theta, such that this ray follows the law of reflection. And we all know how to do this using simple geometry. Okay. Now, this is a symmetric situation. I can draw a completely symmetric about this axis. I can draw a ray coming in this angle at an angle theta. And if I have this mirror AC, AC1, I can redirect that ray to B. So now I have a situation where I have one edge ray, R1, going to A, another edge ray going to B. Now, if I'm able to do this, I know from the edge ray principle that any other rays which come at a smaller angle, anywhere in between, will end up in between these 2 points. Let me redraw that once more. I know for a fact that if I come in at a smaller angle, this ray will go in between. I can come in, I can draw any smaller angle. I will always come in between. And so on and so forth. Of course, if I have a larger angle, it will miss the device. We'll come to that later on. And of course, this is symmetric, right? You can reflect everything about this axis. You will see the exact same situation. Okay, I think you can visualize that. Now, let's take the situation if beta is too small. So I didn't select my the angle of the mirror properly. Now, of course, what happens is that this edge ray will bend at a larger angle, and it will, instead of going to A, it will go to a distance to the left of A. But because I have a symmetric situation, I have a mirror here, that ray will simply escape the system. Okay, so now I can see that if I do not design this angle beta just right, such that the ray R1 ends up at the point B, I will simply lose the ray. Okay, well, we'll see what this means. Now, I want to take a second, and I want you, maybe 30 seconds or so, I want you to think about an answer to this question. Now, I want to increase my entrance aperture somehow, because again, our goal is to, and feel free to discuss if you're in class or chat if you want, but I want you to answer this question. My receiver area is fixed. This AB is fixed. What can I do? And my input ray angles are fixed. So it has a maximum angle of theta. What can I do to increase the concentration? To increase the concentration, if my receiver area is fixed, all I can do is I can increase the entrance aperture, which is where the light comes in. So what can I do to do that? So I want you to all to think about this maybe for 30 seconds or so. And feel free to type in chat what you think should happen. And feel free to talk as well, if you want. Any thoughts? I mean, it should be a little bit common sense, but let's see. Are there any ideas? Jared, let me see, what did you say? You said we can increase the distance from A to B. So, oh yeah, Jared suggested increasing the size of the receiver. Now the receiver is fixed, so let's imagine that's our constraint. That's our solar cell. We can't change it. So what else can we do? We want to increase the collection area where the light's coming in. Any other suggestions? Well, I mean, yes, exactly, yes. So there's a bunch of suggestions. That's great. Adjust angle C. We can change the angle from A to C1. We can change the angle beta. Make C1 and D1 more wide open. Exactly. Yes. You're all correct. So actually, the Weiss made the point I was going to make, which is our goal is to increase the entrance aperture, which is this, right? We want to make that far larger. And of course, to make that larger, I can do something simple. I can just increase this angle, right? That's one way to make that larger. However, we know that that's not such a great idea because you'll start losing the light, which actually I think is in the next slide. Let's Oh, I forgot. So you can try to increase the angle beta, but we know from the previous slide that beta, there is a maximum value to beta. It has to be just right, such that this situation is satisfied. Now, what happens if I bend it more? This light will come hit there, and it will simply reflect off. Right? Or it will hit the other side and reflect off. It will escape the system. There's one particular optimum angle, but I can ensure that this ray ends up right there. So what else can I do? What I can do is I can add more mirrors at a slightly different angle. So I can add another segment of a mirror here, D1, D2, such that the same ray now, not the same ray, sorry, the same angle, or the ray with the same angle ends up at the edge point here. So again, let's see what happened here. This is the original ray we had, and it goes to this edge point here. I added a mirror here, such that I can, and of course I'm adding an equivalent mirror on the other side, such that I'm going from an entrance aperture which looks like that to an entrance aperture which looks like that, which is a little bit bigger. So now I've increased my entrance aperture without changing my receiver size. So I've increased my concentration factor. Now, of course, this angle beta 2 is different than beta 1. Why? Because of the location of this ray, right? It's shifted. So, and I need to ensure that it ends up at A as well. So beta 2 has to tilt a little bit larger with respect to the normal. And you can see that from geometry relatively easily, right? Because it has to bend at a larger angle here compared to here. And I can keep doing this, right? I can keep doing this, keep adding another segment over here, another segment over here, and so on and so forth. I can keep building this up. Let's see what happens. I can keep adding those mirrors. And of course, those mirrors all trace a surface, because I can, in the previous slide, the mirrors were the mirrors were discrete. Like I had these discrete points, but of course I can make it continuous and make it into a curve, right? That's really eventually what will happen, because I can make these segments infinitesimally small. And we know from basic calculus that just follows a curve. In this case, we're tracing a reflective surface or a curve, as shown here. Now, so what does this look like? So again, let's just review what has happened. I've taken every ray, these are parallel rays, okay? And I've defined this reflective surface. So it's like designing that lens as before. I've defined this such that each ray ends up at the same point here, A. So it's exactly same as our design for geometrical optics, where we looked at every ray here, the intersection of that ray with the surface. We drew a normal here. We made sure that the law of reflection is satisfied. Those two angles are the same. And we came up with what this tangent should be. And the same thing here. We figured out, okay, what normal do I pick? Says these angles are the same. And the picking of that normal defines the tangent here. And I do that for every ray. I will form a surface, just like I did in geometrical optics. We will see shortly that that surface is a parabola, but I just want to make sure we also appreciate the symmetry here. So there's a symmetry about this axis, just like before. So I can have the exact same curve on here, which is a mirror symmetry of this curve. My drawing here is not great, but I think you get the picture. So now in this situation, every angle, every point on the curve has its own angle beta that is minimized, and that at that particular point such that this ray redirection happens. I think that's also pretty clear. Now you can show that this is also the curve that produces the smallest beta. You want that to be as small as possible for the largest entrance aperture. So, and the largest entrance aperture. So this is what defines the parabolic concentrator. Now it's a compound parabolic concentrator because there are two of them, at least in 2 dimensions. Of course, in 3 dimensions, it will be rotated, and there are some complications there that we should be aware of. Let's see. Okay. Now, let's think about this. Take this curve here, okay? And I'm going to rotate it in this direction. Rotate it down so we can look at it in a fashion that's more familiar to us. Okay, and that's drawn here. So this is the same curve as before, just rotated a little bit counterclockwise. Clockwise. Now, as before, we said that all edge rays must be reflected onto A. So in the previous slide, I had this A. Sorry, I'm kind of stuck. In any case, coming here. Now here, my A is equivalent to F. Okay, so when I rotated it, my A became F. And my edge rays are now Q1, P1, Q2, P2, Q3, P3. So again, imagine this was rotated on its side. It's the exact same picture as before. I have a ray Q1, Q3, P3 here, gets reflected to F, which was my old A. And any other edge ray Q2, P2 goes to F, Q1, P1 goes to F. Now, FV is now my receiver. That was my AB. Let's see if this, oops, my stylus here is misbehaving. Don't know why. Okay, so in any case, you can see that all these edge rays are focused onto F. That means that the surface now is a parabola, right? And F is the focus of the parabola. So you can see all these parallel rays have to come to F. Now I have an equivalent parabola on the other side, not this. I'm going to put them all together. So keep that picture in mind. Let me see if this. Okay, now it works. Sorry. So again, what I want you to keep in mind is that this is my receiver now. And I'm only going to take this section of the parabola and I'm going to rotate it. Okay, so just keep that in mind. And I'm going to put